So this is my video on 6.2, which is exponential functions. A function of the type a to the x is called an exponential function. Where the thing about exponential function is that the exponent or the variable actually appears in the exponent. So for example, 2 to the x, the variable for the first time it has gone up to the exponent 3 to the x, and even 1/2 to the power x or 1/3 to the power x. All you require is that the base has to be greater than 0. Okay, so now if you look at this one, 2 to the minus x is kind of different, but still it is an exponential function. Why? Because 2 to the x can be written as 1 over 2 to the x, right? And 1 can be written as 1 to the x, right? Over 2 to the x, right? And then 1 and 2 can be brought together in a single fraction, so 1/2 2 to the power x, right? So all these are exponential functions. So the idea is it should be at the form 2 to the x or something, a to the x, where the exponent comes in the variable comes in the exponent. The variable x is in the exponent. So now let's take f of x equals 2 to the x and let's try to get some points. So if you put x equals 2, then you get 2 to the negative 2. So what you do is you go up to x and plug in x equals negative 2. So you get 2 to the negative 2. Okay. And that's 1 over 2 to the 2, and that's 1 over 4, that's 1/4. So at negative 2 it goes to 1/4. Negative 1 it's 2, and you go up to 2 to the, so it's 2 to the x, so you go up to x and plug in negative 1, so you get 2 to the negative 1 and 1 over 2 to the negative 1 and 1 over 2. Okay, so so that's that. And then if you go to 0, you get 2 to the 0. Once again, you go up to x and plug in x, x equals 0, 2 to 0 is 1, right? Which makes you feel that if you plug in any number, the 0th power at 0, right? Regardless of whether this is 2 or 3 or 4 or 5, the 0th power is always 1. So the value of the exponential function at 0 is always 1, okay? The value at 2, where x equals 1, okay, then what you do is you plug in x equals 1 here, and then you get 2 to the 1 equals 2. So you plug in these values, so so you 1/4, 1/2, 1, 2, you can see at negative 2, it's 1/4, it's very small, negative 2 is 1/2, and then at 0, of course, it goes through 1, and then at 2, it goes to 4. So you can see it starts small, but it grows exponentially. So this is why it is called exponential function. It starts slowly, but and the other thing is if you look at, see the quotient between any two of these places, like now here the quotient between 1/4 and 1/2 is 1/4, right? Okay, well, not 1/4, I mean, so it's actually multiplied by 2, right? So 1/4 multiplied to get to 1/2, it's multiplied by 2. 1/2 is multiplied by 2 to get to 1, and 1 is multiplied by 2 to get to 2. So there's always a constant multiple between any of these two. So it actually multiplies so fast because between any two consecutive points, there is a constant multiple. It's multiplied by the same amount. That's why it's called exponential, right? And again, now that's for something like 2 to the x, right? Okay, this is the graph. It looks like 2 to the x. Now, if you consider a graph like 1/2 to the power x, right? It goes the other way around. For example, at negative 2, then you just plug in negative 2 here. You get 1/2 to the power negative 2, which is 1 over 1/2 to the power 2, really, because negative 2 is actually 1 over the positive power. So you get 1 over 1/2 to the power 2 is 1/4. 1 over 1/4 is the same as 4. So as negative 2, it's 4. Likewise, at negative 1, it is 1/2 to the power negative 1, which is 1 over 1/2, which is 2. At 0, it's again 1. At 1, you get 1/2 to the power, you just plug in 1 here, and when you plug in 1 here, you get 1/2 to the power 1, which is 1/2. At 2, you get 1/2 to the power 2, which is 1/2 to the power 2, which is 1/4 and 1/8. So you can see that the numbers are getting smaller. 2, negative 1, 1/2, 1/4, 1/8, right? So it starts high and then at 1 it crosses 1 and goes down very small. Once again, the x-axis is actually now an asymptote. X-axis is an asymptote. Here again, the x-axis is an asymptote. Okay. So let's go down. So can you see the shapes, the difference, right? When the number here is less than 1, right? It's a decay. Okay. And when the number there is greater than 1, we have a growth, which is a growth. So growth and decay, depending on whether the base is greater than 1 or less than 1. So it's a nice graph, show you the different possibilities. For example, you can see that 1/2 to the power x and 1/4 to the power x are all both decays, right? They start from top and they go down, right? Okay, and but on the other hand, if you take something like 1/2 to 2 to the x or something like that, right? So you can they all go through 1, right? So that's like a fixed. So 1/2 x would actually decay. 1/4 would decay, kind of a steeper decay, right? Okay. But if you look at 2 to the x is the growth, and 4th to the x is a steeper growth, and 10 to the x is even a steeper growth. Okay. Okay. So again, what this shows is that when the base is greater than 1, it's a growth. When the base is less than 1, it's a decay. And they all go through the point 1. The y-intercept is 1. So now suppose you want to draw the graph of y equals 2 to the x minus 1. How do you do that? Well, you use transformations. So if you can draw the graph of 2 to the x, which is drawn here in red, okay. Then if you want to get 2 to the x minus 1, what you do is you shift the graph down vertically by 1. Now we are going to, for the very first, would have seen the number e appearing in your college algebra and even previous classes, and really there was no real definition of e, saying that it's 2.7 something or the other. But now we are in calculus, we finally get actually a chance to define e. What happens is, if you look at this limit, you can show by different pure mathematical means that this limit, there is a certain value, right? I mean, okay, so now for this base, okay, so for example, if you just take the a to the, let's see, so if you look at let's try to see if I can draw this again. So if you look at this quotient a to the h minus 1 over h, right, limit as h tends to 0. So h is your variable really, right? And then if you try to put different values for a, okay, so if you try to put like a equals 2 and 3 and try with different values, you know that for a certain value of a, you can show that this is equal to 1 for a particular value of a. That value of a is defined as e. So once again, by trying out different values for a, when you calculate the limit a to the h minus 1 over h as h goes to 0, you can show mathematically that there is one value for a for which this limit is 1. And we call that value, we define that value as e. That because e need to be defined. Okay. All right. So that is e. And so now let's go down, right? Okay. And see what we get for e, okay? And now we can show that if f of x equals e to the x is a very important result, the derivative of that function is e to the x. So once again, we talked about exponential function. So, and we know that For different values of base, right, you can have a growth or a decay, right? And we took this value E, which is a very special value, which is 2.7 something, right? Okay, which means that it is actually greater than 1, so it's a growth. For that value of the base, something nice happens, and that's the derivative of that exponential function is itself. So e to the x, the derivative is e to the x. And what is e? E is a value for which you get a to the h minus 1 equals a to the h minus 1 over h, the limit to be equal to 1. So now let's try to prove this, right? So we know by the definition of the derivative is the limit definition f of x plus h minus f of x over h. So limit h goes to 0. What is f of x of h? So what you do is you go, f of x is e to the x. So what you do is you go and replace the x by quantity x plus h. So x plus h minus f of x is once again e to the x divided by h. So now this is a exponential of a sum, right, which can be broken up as a product. So that is e to the x and e to the h minus e to the x over x, and limit as h tends to 0. So now we take e to the x outside, you get e to the x, and then you get inside. From here, when you take e to the x, you get e to the h. From here, when you take e to the x, you get 1. Okay, and then now remember the limit here is the variable is h. So therefore, e to the x is actually a constant. We can take it outside, right? So e to the x and limit h tends to 0, e to the h minus 1 equals h. But we saw that earlier, we select we select e so that e to the h minus 1 over 1 h is the limit is e to the h minus 1 over h, the limit is 1. So that's how we selected e. So therefore, by definition, this is equal to 1. So when this equals to 1, then you have e to the x equals 1, and you get e to the x as the answer. So the bottom line is if you take the function e to the x, the derivative is e to the x, which is very nice. Now let's try to prove some examples from this. So now we want to differentiate e to the sine x. If you're using chain rule, when you look from outside, you don't see the sine x, you see e to the some junk. So if you differentiate that, you get what? If e to the whatever, the derivative is e to the that thing. So e to the x. So you repeat e to the x, right? And but when you go inside, you see sine x, right? And then you need to multiply by the derivative of that. So that is cosine x. Let's take another example. So if you have e to the x cosine 3x, so now we need to use product rule. So right one is would be e to the 5x times the derivative of the second piece, which is what? Now you use chain rule. From outside, you don't see the 3x, you only see cosine of some junk, right? So the derivative of that will be negative sine 3x, right? But you need to go still inside, and then you will see a 3, and you need to multiply that by 3 plus right 2, which is cosine 3x, and then you need to now go and differentiate e to the 5x. So from outside, you will see e to the some junk. The derivative of that is e to that whatever junk, right? Okay, and then you go inside, you will see 5x, right? And the derivative of 5x is just 5. Okay, you guys okay with that, right? Okay. All right. So now we can take out. We are done with the derivatives, but we can take out e to the 5x, and we take out e to the 5x from here. From here, if you take e to the 5x, we get 5 times cosine 3x. So that's that. 5 times cosine 3x, right? Minus, if you take e to the 5x from here, you're left with a 3 and a sine 3x. So e to the 5x is outside. You get 5 cosine 3x from here minus 3 sine 3x from here. Okay, then that is your answer. So let's do an example 3 where you find the critical points of this, right? And then again, you need to find the derivative. So x product rule, x times the derivative of this would be e to the negative x, and then the derivative that will be e to the negative x repeated. So you repeat whatever this is, right? And then you go inside and multiply by negative 1. So that is e to the negative x times negative 1 times x, right? Plus right 2, which is e to the negative x times the derivative of x is 1. So, and then when you take out e to the negative x, you get a negative, you get 1 from here, okay? And then you get a negative x from here. So you get e to the negative x, 1 minus x is equal to 0. So it's e to the negative x is equal to 0, or x equals 1 minus x is equal to 0, which means what? Or x equals 1. But we know that a to the x, negative x, is a decay and it has a horizontal asymptote at 0, so it's never really 0, okay? So, I mean, if you look at a to the negative x graph, right? Okay, so let's just try to see if I can draw this, right? Okay, so and then because we saw that earlier, right? And so we have that to be equal to, so we can't have e to the minus x equals 0, right? So we must have x equals 1. And you can actually draw that, but if you draw the graph of this function, you can see that there is that at x equals 1, there is a local maximum. Okay, so x equals 1 is the critical point here. Let's do an integration problem, right? Okay, so what's the integral of e to the x? Well, the derivative of e to the x is itself, which means that the integral of e to the x is also e to the x. Okay, all right, so that's very nice. So e to the x doesn't change whether you differentiate it or integrate. The answer is e to the x. So now you need to do integral of x times e to the x squared, right? So how do you do this? So, well, first of all, you can put a substitution here, right? Why will that work? Because the derivative of substitution is 2x and there's an x outside, which actually means that it might work. So you put u equals x squared, right? Then du over dx is equal to 2x, which actually gives you dx is equal to du over 2x. And then if you put that out here, you get I equals, you leave the x alone, right? Because it will cancel off. E to the x squared will become e to the u, du over, and then for dx is nothing but du over 2x, right? So du over 2x, and then if you take out 1 half, the x will cancel off, right? And then if you take out 1 half, you get integral of e to the u du. And the integral of e to the u is itself, right? Like integral of e to the x, so that's e to the u, and you have 1 half outside. And finally, you just take out u equals x squared and plug it in. So as another final example, you want to find the area under the curve e to the minus 2x, right, from x to the 0. So it's a decay, so because it's decay curve, right? Okay. And so all you need to do is straightforward something like this, right? Okay, so say straightforward integration, right? And you just integrate it from a 0 to 1. Okay, so once again, when you integrate e to the negative 2x, well, you can use a substitution and check this, but it's generally easier when you differentiate e to the 2x, you repeat it and multiply by the coefficient here. It's a constant coefficient, right? So we can do the same, right? Okay, so what you do is the coefficient is negative 2. So what you do is instead of multiplying, you do divide by the negative 2, because when you differentiate this, you get a multiple by negative 2. You need to get rid of that. So you divide by negative 2. So it's negative 1 half e to the negative 2x, and the limits are 0 and 1. You put 1 and 0, and then you should get this answer. I want you to check that answer. That's it for this video, right? And we'll see you in a different video, right? Okay, and thank you for watching.